One bourbon, one scotch, and one bill. One bourbon, one scotch.
Okay, so let's start with vertical asymptotes. So how to find, for a general polynomial this is, how to find, we'll start with vertical asymptotes, okay? So this would be where the denominator, and I'll just abbreviate denom for denominator, where the denominator is equal to 0. And, this is an important part, and the numerator, so the top, right? So denominator over numerator, right? That's just the structure of like a ratio or a fraction. And the numerator is not equal to 0. Okay, so what does it mean, like where? That means just your x value or your whatever variable you have. Whatever variable you have makes your denominator equal 0. I just wrote that completely wrong. I can't. Okay, algebra. Woo! Okay, and the numerator is not equal to 0. So, numerator, of course, is the number on top, or your value on top, okay? And then denominator is on the bottom. Okay, whoa, flashbacks to like 4th grade. Okay, so we got it right now. This is the form of a fraction, the proper form, right? So, anyways, what I was saying was where just means like at what x value, at what x value, or whatever variable you have, that this is such that this happens, so that your denominator is equal to 0 and your numerator is not, okay? Alright, so there's another case, so other case, I'll just write in here, other case, when both denominator is equal to 0 and your numerator is equal to 0, then that's kind of a different case, where you can factor and cancel, so you can factor something out, factor as much as you can and cancel out whatever you can, okay? And then if it's still like this, factor and cancel, and if still like this being that both your denominator and numerator are equal to 0, then we have what's called a hole in the graph. Then we have a hole, what's actually called a removable hole, removable, that's just the technical term for it, in the graph, okay? And what does that look like? Kind of just what you would picture it to be. So let me just draw that, I'll just sketch a little bit on the next slide. Okay, so if we were to have, let's say, 1, 2, 3, 1, 2, 3, 4, let's say we had something like this, okay? And something like that. Okay, it might not be that prominent, but anyway, so right here we could see that we have a vertical asymptote, okay? Some vertical line going down. So this is a vertical asymptote. So this would be where denominator is equal to 0, but numerator is not equal to 0, okay? So that's where we're undefined, okay? And then right here at this value, we actually have a removable hole. So this is the hole, or the removable hole we talk about, okay? So this is when numerator is equal to 0 and your denominator is equal to 0, okay? Alrighty, now for horizontal asymptotes. Okay, so how to find, and now we'll do horizontal asymptotes. Okay, so there are 3 different cases that we could run into with horizontal asymptotes. Okay, so case number 1. So we have when the degree, meaning the highest power of your denominator, is greater than the degree, meaning the highest power, in your numerator, then let's say, for example, we have, let's say, f of x is equal to a 3x plus 2 over x squared plus 4x, I don't know, minus 5 or something like that. Okay? Let's say we have something like this. Then in the long run, remember horizontal asymptotes are studying what happens to your graph in the long run. So in the long run, our to exemplify long run, f of x is going to be about equal to what? And that would be obtained by kind of canceling out all of the lower non-leading terms in your upper and your lower polynomials, okay? So upper meaning like the one on top, and then lower just meaning the one on the bottom, right? So you know how for any polynomial, for any given polynomial, the long run behavior is determined by the leading term, right? So the leading term on top is this 3x, and the leading term on the bottom is this x squared. So f of x is overall going to look like this in the long run, okay? And we can cancel out an x on top and bottom, so we get 3 over x. And this, in the long run, this behaves like our 1 over x graph, okay? So this is going to go to 0 in the long run, okay? So that basically just means, okay, so f of x, or we could even say y, is equal to 0. This gives us a horizontal asymptote whenever we're in case 1, which is when the degree of the denominator is greater than the degree of the numerator, okay? And not only for this example here, that also happen if you have like x over x squared. Well, that's what we had. Okay, let's say x over x cubed, same concept happens in the long run, and anytime you have this case number 1, okay? Alrighty, so now for horizontal asymptotes, case number 2. Case number 2. So what is case number 2? It'll just be the opposite. So when the degree of the denominator is less than the degree of the numerator, okay? Then let me give you an example so we can see what goes on. So 3x squared plus 2, let's say, over, I don't know, x like minus of 5. Okay, so in the long run, again, because we're looking in the long run for our horizontal asymptotes, so in the long run, as our x goes to positive and negative infinity, so either way, our f of x is, so let's find the leading terms, right? So, and this is f of x is equal to, okay, so the leading term on the top is just this 3x squared, so we can kind of ignore everything else in the long run. The leading term on the bottom is this x, so f of x ultimately looks like 3x squared over x, which simplifies to 3x, okay? And as x goes to negative infinity, this is going to go to negative infinity, and as x goes to positive infinity, our f of x is going to go to positive infinity as well, right? So let me just write that down. So as x goes to negative infinity, we're just going to plug in a negative infinity for x, so f of x also goes to negative infinity. This is just the equation for a line, right? And as x goes to positive infinity, our function value goes to positive infinity. So we see, okay, so there's not really, there's no horizontal asymptote, okay? Because we see that we have something like this, right? It's going up and down. There's no place where it levels off in the long run, okay? So there is no horizontal asymptote, okay? When we have case number 2, which is when the degree of the bottom of the denominator is less than the degree of the numerator, okay? Now, for case number 3, for horizontal asymptotes, you probably guessed it by now, maybe by process of elimination, but this would be when the degree of the denominator is exactly equal to the degree of the numerator, okay? And again, just a refresher, the degree just means the highest power of a polynomial, right? So here's an example again. So let's say we have f of x is equal to 3x squared plus 2 over, let's say, x squared plus 4x and then minus our 5. Okay, so let's look at this. So we have as, in the long run, as x goes to, I don't know, positive and negative infinity, we have that f of x goes to what? So let's find the leading term. So this is the leading term on the top, and this is the leading term on the bottom, right? So we're going to have some kind of thing that looks like this, where we see that, wow, the x squareds both cancel, because they happen to have the same degree, right, on top and bottom. So what we actually end up with is something like this, and this is equal to y. So this gives us our horizontal asymptote. And the thing is, so the overall, like, more general formula would be saying that, well, so since we have y equals 3, so this is our horizontal asymptote, right? So the horizontal asymptote, when our degrees on both the top and the bottom are equal, would be given by the ratio of leading coefficients, okay? Coefficients. And you don't do anything fancy. You just take whatever you have and you look at the coefficients and you say, okay, so our horizontal asymptote is going to be 3 over 1, or like y equals 3 over 1, which is the same thing as y equals 3, okay? Alrighty, so let me just draw a quick chart here. So we're going to say, okay, so degree of denominator here, okay, and then degree of numerator here. Alrighty, and then what happens with our horizontal asymptote? So for the first one, let's say we have, let me make 3 little lines here. That was a really horrible line, so let me try drawing that again. Okay, so if we have that the degree of the denominator is greater than the degree of the numerator, then we have that the bottom is going to be growing faster than the top, right? Which means that our horizontal asymptote is going to be y equals 0. Okay, it's going to zero out. Our function is going to zero out at some point. Okay, and then we have, let's see what else. We could have the other case where the denominator's degree is smaller than the numerator's, and then therefore we don't have any horizontal asymptotes because our function either goes to infinity or negative infinity. Okay, and then the last case was if they're equal, then you just look at y is equal to the ratio of leading coefficients. Okay, and those are our 3 cases that we've gone over. Okay, so here's an example. We have find the horizontal and vertical asymptotes of this function. So in order to find the vertical asymptotes, we need to find for what x values make denominator equal 0, but not the numerator. Okay? So in order to find that, we just say, okay, so for the denominator to be 0, we could have x equals 1, and then we just check. Okay, does that make the top equal 0? No. So that's a good one. How about x equals negative 2? If we were to plug a negative 2 into the top, that wouldn't equal 0, so we're good there. And x equals 5. And then if you plug that into the top, that does not equal 0 either. Okay, so we're good there. So those are our vertical asymptotes. Okay, and then for our horizontal asymptotes, let's see what would happen here. So overall, our leading term on the top is going to look like the following. So we would have f of x is equal to x squared of some sort, right? So this is in the long run. And then over x to the third of some sort. So comparing the degrees on the numerator and the denominator, we see that the degree of the denominator, so degree of denominator, is greater than the degree of the numerator. So this gives us case number 1. Okay, and you don't have to remember like which numbered case it is. You just have to remember, okay, so when this happens, then we have that our horizontal asymptote is going to be y equals 0. Okay, and that is it. Okay, so here's the same function that we were working with before, but now what we're going to do is find the intercepts of it. Okay, so let's start off with vertical intercepts. So vertical intercepts happen when our input, so in this case x, is equal to 0. Okay, so let's just find that. So we have f of 0 is equal to 0 minus 2 times 0 plus 3 over 0 minus 1, 0 plus 2, and 0 minus 5. Okay, so if we just multiply these out, we just get negative 2 times positive 3, so that's a negative 6. And then over negative 10, so that would be a positive 10. So this simplifies to a negative 3 over 5. And our vertical intercept, the way you would write it as a point is just 0, negative 3 over 5. Okay, so that's the vertical intercept. And now to find the horizontal intercept, this is when our function is equal to 0. Okay? So this would be, and just rewriting this, so this would be x minus 2 times x plus 3 over that whole stuff on the bottom. Okay, so the bottom can never, it doesn't really contribute to having a function value of 0, because even if the bottom were equal to 0, that would just mean your function's undefined, which tells you your vertical intercepts, right? So in this sense, we don't really care about the bottom at all. The top is what's going to allow our function to go to 0. So we just set the top equal to 0, okay? And we find x is equal to 2 is one of them, and x is equal to negative 3 is another. So we could say that our horizontal intercepts are going to be 2, 0, as well as negative 3, 0. Okay, and just a reminder, you can have multiple or none horizontal intercepts, but you can only have at most one vertical intercept because we're working with functions, right? And for each x value, or for each input, you can only have one output.